You've probably heard the CPU called the brain of a computer. It's a really simple idea, right? But it hides this world of just incredible complexity. So today, we're going to peel back the layers and take a look inside at the architecture, the rivalries, and the sheer power that makes your entire digital world tick.
So, what is really going on inside that little chip? I mean, what are the fundamental rules and the big rivalries that actually determine how fast you can edit a video, or load up a game, or heck, even just open a new browser tab? Well, let's dive in and find out.
You know, every single processor starts with a plan. Long before a single bit of silicon is touched, engineers map out its entire design. We call this its architecture, and it is, without a doubt, the single most important factor that defines what a CPU is and what it can do.
Think of CPU architecture like the blueprint for a huge skyscraper. That blueprint doesn't just show you what the building's going to look like. No, it dictates everything. Where the foundation goes, how the electrical systems are wired, the plumbing, the elevators. A CPU's architecture does the exact same thing. It lays out where all the core components go, what kind of instructions it can even understand, and how data is going to flow through it.
So this architectural blueprint, it determines some absolutely crucial things. It sets the bit size. Think of that as the width of the data highway, whether it's 32 lanes or 64. It defines the registers, which are like these tiny, super fast scratch pads for calculations. It even designs the pipelines, which act like super efficient assembly lines for executing instructions. This is exactly why software made for one chip family just won't run on another. Their fundamental blueprints are completely different.
But here's the thing. These architectural blueprints, they don't exist in a vacuum. They're born into a fiercely competitive market. And for decades, the story of the PC's processor has really been the story of an intense rivalry between two titans of the industry.
On one side, you've got Intel. They are the historic leader, the company that literally created the world's first microprocessor, the 4404, and whose 8086 chip powered the original IBM PC. They set the standard for decades. And on the other side, Advanced Micro Devices, you know 'em as AMD. They started out making more budget-friendly chips, but through just relentless innovation, they have become a true competitor whose products often challenge and sometimes even beat their Intel rivals. And honestly, that competition has been amazing for all of us.
Now, while Intel and AMD absolutely dominate the PC world, they aren't the only players who've made a mark. For years, Apple decided to carve its own path, partnering with companies like Freescale, a Motorola spinoff, to create the really powerful G4 PowerPC chips. But to take things to the next level, Apple then went and partnered with a true titan, IBM.
And that partnership, wow, it produced the G5 processor, which was a landmark achievement. This was the first chip to bring 64-bit computing into the hands of mainstream consumers. And this wasn't just some numbers game. It was a revolutionary leap. It allowed computers to access way more memory, setting the stage for the complex, powerful applications we all depend on today.
Okay, so we have all these different companies and all these different architectures, all fighting for the top spot. But how do we actually compare them? How can we measure performance in a way that just cuts through all the marketing hype and gets to what really makes one processor faster than another?
Well, performance really comes down to a delicate balancing act. You've got raw processor speed, sure, but that's pretty useless without fast access to data, and that's where the cache size comes in. The CPU then juggles that data in its internal registers, and the bit size determines how big each chunk of data is. And then, all of this has to talk to the rest of the computer through the bus speed. A bottleneck in any one of these can just cripple the whole system.
So for a long time, the name of the game was just speed. Speed, speed. But eventually, engineers started hitting the physical limits of raw clock speed. They had to get more creative. Instead of just trying to make the processor think faster, they came up with ways to make it think about more things all at once. Welcome to the world of parallel processing.
So how does a processor handle more at once? It really starts with how data moves around. Serial communication is like a single-lane country road. One bit has to follow the one in front of it. It's slow. Parallel communication, on the other hand, that's like a massive, multi-lane superhighway with tons of bits traveling all at the same time. This is why all the important internal pathways in a computer are built for parallel speed.
So, we can take that more lanes idea and apply it not just to data, but to the processors themselves. This is what we call parallel processing, using multiple cores or multiple processors to work on a problem at the same time. It's the difference between one person trying to solve a giant puzzle and a whole team working on different sections all at once.
A really common way this is done is called symmetric multiple processing, or SMP. This is what you'll find in a lot of high-end desktops and servers. The key thing here is that the number of processors, or cores, is usually a power of 2, so you'll see 2, 4, 8, and so on. They all share the same memory, they all work together. It's a balanced, symmetric system.
But what if you take that idea and just blow it up to an absolutely extreme scale? That's when you get to massively parallel processing. We're not talking about 2 or 8 processors anymore. We are talking about thousands, sometimes tens of thousands of processors, all networked together, working in unison. This is the powerhouse architecture behind the world's biggest mainframes and supercomputers, doing everything from modeling our climate to simulating the entire universe.
All right, and an incredibly powerful CPU is fantastic, but it's totally useless if it can't communicate with the outside world. It can't just sit in a box by itself. So for our last section, let's zoom out from the processor itself and look at how it actually connects to all the devices we use every day. Keyboards, cameras, printers, all of it.
You know, for a while there, it was kind of a wild west of connection standards. You had specialized ports like FireWire, mostly for video gear, and SCSI for super fast hard drives. Laptops had their own thing with PC cards. But then, one standard came along and basically conquered all of them for everyday use, the Universal Serial Bus, or as we all know it, USB.
So why did USB win that war? Well, its design was just remarkably versatile. A single USB port on your computer can, in theory, connect to this many devices at once, 127. That incredible flexibility is exactly why it became the standard we all use today.
These modern ports also brought us an innovation that we completely take for granted now, being hot swappable. The ability to just plug in a flash drive or a camera without having to shut down and restart your entire computer. It seems so obvious now, but back then it was a revolutionary leap in usability, a real game changer.
And the magic behind that seamless experience is a standard called Plug and Play. It's the technology that lets your computer automatically see a new device, figure out what it is, and just get it working, all without you needing to be some kind of technical expert. Honestly, this is the technology that truly made personal computers accessible to everyone.
And this brings us to a really fascinating final thought. If the CPU is the brain and the ports are its senses, its eyes and ears, the brain has always been faster. But today, with ridiculously fast storage and networking, we're facing a brand new challenge. For the first time, our computer's senses are becoming faster than its brain. And how our CPU architecture evolves to solve that bottleneck, well, that's what's going to define the entire next generation of computing.